2.5 million light years away. A galaxy 4 times larger than our own is racing toward us at 250,000 miles per hour. The Andromeda galaxy contains 1 trillion stars, countless worlds, and mysteries that challenge everything we thought we knew about the universe. Today, we witness stellar nurseries where baby stars are born in cosmic violence. Explore planets where diamonds rain from methane skies and encounter black holes so massive they could swallow our entire solar system in seconds. Our journey takes us through cosmic storms, past gravitational whirlpools, towards civilizations that might have risen and fallen 1 billion years before Earth even existed. Prepare yourselves, we begin. Our spacecraft engines ignite with the power of 1,000 suns as we break free from Earth's gravitational embrace. The blue marble that has been humanity's home for millions of years shrinks to a pale dot behind us, then disappears entirely into the cosmic darkness. We are now truly alone in the void, beginning the longest journey any conscious being has ever attempted. The first challenge hits us immediately, the sheer scale of what we're attempting. To reach Andromeda, we must travel a distance so vast that light itself, moving at 186,000 miles per second, takes 2.5 million years to make this journey. If we could drive there in a car at highway speeds, never stopping, never sleeping, it would take us 30 billion years. The dinosaurs would still be ruling Earth when we finally arrived. But we have technology beyond current human imagination. Our vessel bends space and time around itself, creating a bubble of warped reality that allows us to slip between the normal rules of physics. We accelerate not through space, but through the fabric of space-time itself. The stars around us begin to shift and blur as we approach speeds that would have been impossible just moments before. As we leave our solar system behind, we pass through the Kuiper Belt where ancient chunks of ice and rock drift in eternal darkness. These are the leftover building blocks of our solar system, frozen in time for 4 billion years. Pluto, once considered our 9th planet, appears as a lonely sentinel guarding the edge of everything we've ever known. Beyond Pluto lies the Oort cloud, a spherical shell of icy objects that extends nearly a light yet from our sun. This is where comets are born, in the frigid depths where temperatures drop to just a few degrees above absolute zero. We are entering a region where the sun's influence barely reaches, where the space between objects is so vast that collision is nearly impossible. The nearest star to our sun, Proxima Centauri, glows like a red ember in the distance. It would take conventional spacecraft over 70,000 years to reach it, but we pass it in what feels like minutes. We are now in interstellar space, the vast emptiness between star systems where matter is so sparse that you could travel for millions of miles without encountering a single atom. This is where most space travelers would feel the crushing weight of isolation, but we push forward with purpose. The Andromeda galaxy beckons from across the cosmic ocean, its spiral arms slowly rotating in a dance that has continued for billions of years. We are no longer bound by the limitations of our species or our world. We're explorers of the infinite, and our destination contains wonders that will challenge every assumption we've ever made about reality itself. The real journey is just beginning. The nearest star to our Sun, Proxima Centauri, glows like a red ember in the distance. It would take conventional spacecraft over 70,000 years to reach it, but we pass it in what feels like minutes. We are now in interstellar space. The vast emptiness between star systems, where matter is so sparse that you could travel for millions of miles without encountering a single atom. This is where most space travelers would feel the crushing weight of isolation, but we push forward with purpose. The Andromeda galaxy beckons from across the cosmic ocean, its spiral arms slowly rotating in a dance that has continued for billions of years. We are no longer bound by the limitations of our species or our world. We are explorers of the infinite, and our destination contains wonders that will challenge every assumption we've ever made about reality itself. The real journey is just beginning. We enter the local void, a region of space so empty it defies comprehension. Here, between the galaxy clusters, matter exists in concentration so low that an entire cubic meter of space might contain only a single atom. The temperature drops to just a few degrees above absolute zero, and the only light comes from distant galaxies billions of light years away. This is cosmic loneliness on a scale that breaks human understanding. If Earth were placed in the center of this void, our night sky would be completely black except for the faint glow of the Milky Way itself. No other galaxies would be visible to the naked eye. Ancient civilizations would have developed entirely different mythologies, religions, and scientific theories about the universe based on this profound isolation. But the void is not truly empty. Dark matter, the mysterious substance that makes up 85% of all matter in the universe, forms invisible scaffolding throughout this region. We cannot see it directly, but its gravitational influence shapes the very fabric of space-time around us. Our instruments detect its presence through subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang itself. As we travel deeper into the void, we encounter something unexpected: rogue planets ejected from their home solar systems by gravitational interactions with passing stars. These orphaned worlds drift through the darkness, no longer warmed by any sun, their surfaces frozen solid, and their atmosphere is collapsed into ice. Some of these planets are larger than Jupiter, others smaller than Earth, but all share the same fate of eternal wandering through the cosmic deep. One rogue planet we encounter tells a particularly haunting story. Its surface shows evidence of ancient oceans, now frozen into ice sheets kilometers thick. Beneath that ice, our scanners detect something remarkable: a subsurface ocean kept liquid by the planet's own radioactive decay. In this hidden sea, completely isolated from any star's light, primitive life forms might still exist, evolved from organisms that survived their world's ejection into space billions of years ago. The void also contains the remnants of ancient galaxy collisions. Tidal streams of stars, stretched across millions of light years, mark the paths where smaller galaxies were torn apart by the gravity of larger ones. These stellar graveyards tell the violent history of cosmic evolution, where galaxy clusters grow by cannibalizing their smaller neighbors in a process that continues to this day. We pass through regions where the cosmic web itself is visible. Vast filaments of dark matter and ordinary matter that connect galaxy clusters across hundreds of millions of light years. These structures formed in the early universe. When matter first began to clump together under the influence of gravity, they are the highways along which galaxies travel. The channels through which matter flows from one region of the universe to another. The silence here is absolute, broken only by the faint whisper of cosmic rays. High-energy particles traveling at nearly the speed of light, accelerated by unknown processes in the violent hearts of distant galaxies. Something magnificent appears in the distance. A galaxy cluster containing hundreds of individual galaxies, each one our island universe in its own right. The Virgo cluster spans 13 million light years across space, containing more than 1,300 galaxies bound together by gravity in a cosmic dance that has continued for billions of years. As we approach this stellar metropolis, the scale becomes overwhelming. Each galaxy contains hundreds of billions of stars, and many of these galaxies are larger than our own Milky Way. Some are elegant spirals with arms that sweep through space like frozen fireworks. Others are massive ellipticals that glow with the combined light of 1 trillion ancient suns, and still others are irregular dwarfs, twisted and distorted by the gravitational pull of their larger neighbors. The largest galaxy in the cluster, Messier 87, dominates the central region like a cosmic giant. This massive elliptical galaxy contains over 1 trillion stars and harbors one of the most powerful black holes ever discovered. The black hole at its center is so massive that it contains the equivalent of 6.5 billion suns, and it's actively feeding on surrounding matter, creating jets of plasma that shoot out from its poles at nearly the speed of light. These jets extend for thousands of light years, creating a cosmic lighthouse that can be seen from billions of light years away. The energy released by matter falling into this black hole is so enormous that it heats the surrounding gas to millions of degrees, creating a hot, glowing atmosphere that pervades the entire galaxy cluster. Between the galaxies, we discover an invisible ocean of superheated gas, heated to temperatures of 50 million degrees Celsius by the gravitational energy of the cluster itself. This intergalactic medium contains more matter than all the stars in all the galaxies combined, yet it's so diffuse that it's completely invisible to the naked eye. Only our most sensitive instruments can detect its presence through the X-rays it emits as it radiates away its enormous heat. The cluster is also filled with dark matter, which makes up about 85% of all the matter here. This mysterious substance forms an invisible scaffolding that holds the entire cluster together, preventing the galaxies from flying apart despite their enormous speeds. Some galaxies are moving through the cluster at over 1,000 kilometers per second, fast enough to travel from Earth to the Moon in just 6 minutes. As we navigate through this cosmic city, we witness ongoing galactic interactions. Smaller galaxies are being torn apart by tidal forces, their stars stripped away to form long streamers that will eventually be absorbed by larger galaxies. This is galactic cannibalism on a massive scale, where the strong devour the week in a process that has shaped the evolution of galaxies since the early universe. The gravitational forces here are so intense that they bend light itself, creating gravitational lenses that magnify and distort the images of even more distant galaxies lying behind the cluster. We witness something extraordinary. Two galaxies locked in a gravitational death spiral, their collision unfolding over hundreds of millions of years. The Antony galaxies, once separate and distinct, are now merging in a cosmic catastrophe that will reshape both systems completely. Their spiral arms have been stretched and distorted into long tidal tails that extend for hundreds of thousands of light years, resembling the antennae of a cosmic insect. The collision zone is a stellar nursery of unprecedented violence. Gas clouds from both galaxies are smashing together at speeds of hundreds of kilometers per second, compressing and heating the interstellar medium until it reaches temperatures where new stars can form. The rate of star formation here is 10 times higher than in normal galaxies, creating brilliant clusters of young, hot stars that burn with the intensity of blue, white diamonds. But star formation is not the only consequence of this cosmic collision. The gravitational chaos is also feeding the supermassive black holes at the centers of both galaxies. As gas spirals inward toward these cosmic monsters, it heats up and glows with X-ray radiation, creating some of the brightest objects in the universe. These active galactic nuclei pump enormous amounts of energy into their surroundings, creating jets of plasma that extend far beyond the visible galaxies themselves. The merger is also creating something entirely new: globular clusters, dense balls of stars that will survive long after the collision is complete. These stellar cities contain hundreds of thousands of stars packed into regions just a few dozen light years across. They are among the oldest objects in the universe, and new ones are being born in the chaos of this galactic collision. As we watch this cosmic catastrophe unfold, we realize we are seeing the future of our own galaxy. In approximately 4 billion years, the Milky Way will collide with the Andromeda galaxy in a similar cosmic dance. A collision will take place over hundreds of millions of years, gradually reshaping both galaxies into something entirely new. The space between the colliding galaxies is not empty. It is filled with streams of stars that have been torn from their home galaxies by tidal forces. These stellar refugees will wander through intergalactic space for billions of years, no longer bound to any particular galaxy. Some will eventually be captured by other galaxies, while others will drift alone through the cosmic void forever, despite the apparent violence of the collision. Individual stars rarely collide with each other. The distances between stars are so vast that most will simply be redistributed into new orbits around the merged galaxy's center. However, many planetary systems will be disrupted, their planets flung into new orbits or ejected from their home systems in time. The collision is also creating something beautiful. Shock waves that compress the interstellar medium and cause it to glow with brilliant colors. These cosmic fireworks paint the merger zone in shades of red, blue, and green, creating one of the most spectacular sights in the universe. We encounter our first truly alien world, a planet orbiting a binary star system where the very nature of day and night challenges everything we thought we knew about planetary environments. This world, twice the size of Earth, experiences a complex cycle of illumination as it orbits two stars locked in their own gravitational dance. The primary star is a yellow dwarf similar to our Sun, but its companion is a red dwarf that burns with cooler, dimmer light. As the planet moves through its orbit, it experiences periods of single-star days, double-star days, and even brief eclipses when one star passes in front of the other. The result is a world where the concept of a standard day has no meaning, where the inhabitants must adapt to constantly changing patterns of light and darkness. The planet's surface reflects this chaotic illumination cycle. Vast regions are covered in crystalline formations that act like natural solar collectors, gathering and storing light energy during the brightest periods and releasing it slowly during the darker phases. These crystal forests create a landscape that shimmers and glows with accumulated starlight, painting the world in constantly shifting colors. The atmosphere here is unlike anything in our solar system. It contains high concentrations of noble gases that create spectacular auroras when charged particles from the binary stars interact with the planetary magnetic field. These auroras are not confined to the polar regions like on Earth. They dance across the entire sky in ribbons of green, purple, and gold that can be seen even during the day. Life on this world has evolved in remarkable ways. The dominant species are silicon-based organisms that incorporate the planet's crystals into their biological structures. They can photosynthesize using light from both stars simultaneously, making them incredibly efficient at converting stellar energy into biological energy. During the double star periods, they grow rapidly, storing excess energy in specialized organs. During the darker periods, they enter a state of reduced activity, living off their stored energy reserves. The planet's oceans are equally extraordinary. They contain dissolved minerals that make the water slightly luminescent, creating seas that glow with their own internal light. Underwater, entire ecosystems have evolved around chemosynthetic organisms that derive energy from the planet's geological activity rather than from starlight. These deep-sea communities exist in complete independence from the surface world, thriving in eternal darkness beneath the glowing waters. The binary star system itself is evolving. The two stars are slowly spiraling inward toward each other, their orbital decay caused by the emission of gravitational waves. In approximately 2 billion years, they will merge in a spectacular collision that will briefly outshine entire galaxies. When that happens, this remarkable world will be vaporized in seconds, its complex ecosystems and beautiful crystal landscapes reduced to their component atoms. But for now, the planet continues its complex dance around its twin suns, a testament to the incredible diversity of worlds that exist in the universe. As we leave this system behind, we carry with us the knowledge that life finds ways to adapt to conditions that would seem impossible to Earth-based organisms. We approach a stellar graveyard where the remnants of dead stars create one of the most dangerous regions in the galaxy. Here, neutron stars, the collapsed cores of massive stars that exploded as supernovae spin at incredible speeds while generating magnetic fields trillions of times stronger than Earth's. One neutron star captures our attention immediately. It's only 20 kilometers across, smaller than most cities, yet it contains more mass than our entire sun. A single teaspoon of neutron star material would weigh 6 billion tons on Earth. The gravity here is so intense that the escape velocity is nearly half the speed of light, and time itself runs noticeably slower than in normal space. This particular neutron star is a pulsar spinning 30 times per second while beaming lighthouse, like streams of radiation from its magnetic poles. Each pulse arrives with clockwork precision, more accurate than the most precise atomic clocks humans have ever built. The beams sweep across space like the rotating beam of a lighthouse, and when they point in our direction, our instruments detect bursts of radio waves, X-rays and gamma rays. The space around the pulsar is filled with a wind of charged particles accelerated to nearly the speed of light. This pulsar wind creates a bubble of high-energy plasma that extends for light years in all directions, heating the surrounding interstellar medium to millions of degrees and creating a glowing nebula that can be seen from thousands of light years away. As we maintain a safe distance, we observe the pulsar's incredible power. In just 1 second, it releases more energy than our sun produces in an entire month. This energy comes from the neutron star's rotation. It's literally spinning down, converting its rotational energy into the radiation that we detect as pulses. Over millions of years, the pulsar will gradually slow down until it becomes a quiet, dark neutron star, invisible except for its gravitational effects. Near the pulsar, we encounter something even more exotic, a magnetar, a neutron star with a magnetic field so strong that it defies comprehension. The magnetic field here is quadrillion times stronger than Earth's magnetic field, powerful enough to strip electrons from atoms at a distance of 1,000 kilometers. If you could somehow survive getting within 1,000 kilometers of a magnetar, the magnetic field would distort your atoms, stretching them into thin shapes aligned with the field lines. Magnetars are rare and unstable. They occasionally experience star quakes, sudden rearrangements of their crystalline crusts that release more energy in 1/10 of a second than our sun produces in a year. These star quakes create bursts of gamma rays so intense that they can affect Earth's atmosphere from thousands of light years away. The region also contains isolated black holes, stellar corpses so dense that nothing, not even light, can escape their gravitational pull. These invisible monsters can only be detected by their gravitational effects on nearby matter, creating accretion disks of superheated gas that spiral inward while glowing with X-ray radiation. This is where massive stars come to die, creating some of the most extreme environments in the universe. We enter a region where space itself seems to be boiling with energy. Here, the fabric of space, time is constantly fluctuating with quantum foam, virtual particles that pop into existence and annihilate each other in time frames so brief that they seem to violate the conservation of energy. This is the quantum vacuum, and it's anything but empty. At the smallest scales, Space and time become grainy and uncertain. The smooth fabric of space, time that we experience in everyday life, breaks down into a churning sea of quantum fluctuations. Virtual photons, electron-positron pairs, and other exotic particles constantly appear and disappear, borrowing energy from the vacuum itself and paying it back before the universe notices the dead. These quantum fluctuations have real, measurable effects. They create a subtle force called the Casimir effect, where two parallel plates placed very close together in vacuum will experience an attractive force due to the quantum fluctuations of the electromagnetic field. The space between the plates contains slightly fewer virtual photons than the space outside, creating a pressure difference that pushes the plates together. As we travel deeper into this quantum realm, we encounter something extraordinary. A region where the expansion of the universe itself is accelerating. Dark energy, the mysterious force that makes up 70% of all energy in the universe, is stretching space itself at an ever-increasing rate. This cosmic acceleration means that distant galaxies are moving away from us faster and faster, and eventually they will recede so quickly that their light will never reach us. The nature of dark energy remains one of the greatest mysteries in cosmology. It might be a property of space itself, a quantum field that permeates all of reality, or something even more exotic that we don't yet understand. What we do know is that it's winning the cosmic battle against gravity, driving the universe toward a cold, dark future where galaxies will be isolated islands in an ever-expanding sea of emptiness. In this region, we also encounter cosmic strings, theoretical one-dimensional defects in space-time that might have formed during the first moments after the Big Bang. These cosmic strings are thinner than a proton, but can stretch across entire galaxies, containing enormous amounts of energy and creating gravitational effects that can bend light and distort space around them. If cosmic strings exist, they would be among the most exotic objects in the universe. They would vibrate like guitar strings, creating gravitational waves that could be detected by future generations of instruments. Some theories suggest that cosmic strings could even be used as cosmic highways, allowing advanced civilizations to travel vast distances by following the strings through space. The quantum vacuum also contains the possibility of spontaneous symmetry breaking, where the fundamental forces of nature might suddenly change their properties. This could create bubble universes with different physical laws, where the speed of light, the strength of gravity, or even the number of spatial dimensions might be different from our own universe. Here, at the intersection of quantum mechanics and cosmology, we glimpse the deepest mysteries of existence itself. We discover a cosmic phenomenon that challenges our understanding of physics itself, a region where time flows differently due to extreme gravitational fields. Here, the curvature of space, time is so severe that hours pass like minutes, and the very concept of simultaneous breaks down completely. The source of this temporal distortion is a rotating black hole of intermediate mass, spinning so rapidly that it drags space, time around with it like honey. This effect, called frame dragging, creates a region where it's impossible to remain stationary relative to distant stars. Everything in the vicinity is forced to rotate along with the black hole, caught in a cosmic whirlpool of twisted space, time. As we approach the Earth's sphere, the region outside the black hole's event horizon, where space, time is being dragged around, we experience something unprecedented. Our clocks begin to run slow compared to the time we left behind. Minutes stretch into hours, and hours into days. If we were to spend just 1 hour in the deepest part of the Earth's sphere, decades would pass in the outside universe. The black hole itself is a monster containing the mass of 10,000 suns, compressed into a region smaller than a city. Its event horizon, the point of no return, appears as a perfect sphere of absolute blackness, surrounded by a swirling disk of superheated matter that glows with the intensity of 1 billion stars. This accretion disk is where matter spirals inward toward its doom, heating up to temperatures of millions of degrees as it falls toward the black hole. But the most remarkable feature of this system is the jets of plasma that shoot out from the black hole's poles at 99% of the speed of light. These relativistic jets extend for thousands of light years, creating cosmic beacons that can be seen from across the universe. The energy for these jets comes from the black hole's rotation itself, through a process that extracts energy from the spinning space-time around the black hole. Near the black hole, we encounter something that shouldn't exist. According to our current understanding of physics, matter that appears to be falling upward, away from the black hole's gravity. This is an illusion created by the extreme curvature of space-time, where the very concepts of up and down lose their meaning. What we're seeing is matter following geodesics, the straightest possible paths through curved space-time that appear curved to our outside perspective. The gravitational field here is so strong that it creates multiple images of distant objects. Through gravitational lensing, stars behind the black hole appear as rings of light, their images distorted and magnified by the black hole's gravity. We can see the same star from multiple angles simultaneously, as light from the star follows different paths around the black hole to reach us. In this region, the fundamental nature of space and time becomes apparent. They are not separate entities, but part of a single unified space, time fabric that can be stretched, compressed, and twisted by the presence of matter and energy. The black hole is not just an object in space. It is a wound in the fabric of reality itself. We encounter the most beautiful and terrifying sight in the universe, a star in the process of dying, its outer layers being blown away in a spectacular planetary nebula that paints space in brilliant colors. The dying star, a white dwarf no larger than Earth, but containing the mass of our sun, sits at the center of an expanding shell of glowing gas that stretches for light years in all directions. The nebula itself is a masterpiece of cosmic art. Shells of different gases glow in distinct colors: hydrogen in red, oxygen in green, and blue nitrogen in deep red, creating intricate patterns that resemble flowers, butterflies, or abstract sculptures. These colors are created by the intense ultraviolet radiation from the white dwarf, which ionizes the surrounding gas and causes it to fluoresce like a cosmic neon sign. The white dwarf at the center is the exposed core of what was once a star similar to our Sun. For billions of years, it burned hydrogen and helium in its core, maintaining a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. But eventually, the fuel ran out and the star began its death throes. As the nuclear fires died down, gravity began to win the battle. The star's core collapsed, while its outer layers expanded, creating a red giant that was hundreds of times larger than the original star. For millions of years, the red giant pulsed and varied in brightness, shedding its outer layers in a series of stellar winds that created the beautiful nebula we see today. The white dwarf itself is an object of incredible density. A cubic centimeter of white dwarf material would weigh as much as a car on Earth. The surface gravity is so intense that a person standing on a white dwarf would weigh about 1,000,000 times more than they do on Earth. The surface temperature is over 50 Zarosan degrees Celsius, hot enough to ionize any material that comes near it. But this white dwarf is not alone. It has a companion star, a red dwarf that orbits close to the Earth. A red dwarf that orbits close enough to have matter stripped away by the white dwarf's gravity. This stolen matter spirals inward, forming an accretion disk that glows with X-ray radiation. Periodically, enough matter accumulates on the white dwarf surface to trigger a thermonuclear explosion, a nova that can briefly outshine entire galaxies. The nebula is also a recycling plant for the universe. The gas being expelled contains heavy elements forged in the dying star's core: carbon, nitrogen, oxygen, and other elements essential for life. These elements will eventually be incorporated into new stars and planets, continuing the cosmic cycle of death and rebirth that has been ongoing since the first stars formed billions of years ago. As we watch this stellar death unfold, we are witnessing the fate that awaits our own sun. In about 5 billion years, the sun will expand into a red giant engulfing the inner planets before finally shedding its outer layers and leaving behind a white dwarf surrounded by a planetary nebula that will glow for thousands of years. We drift into a region where space itself becomes a lens, bending and focusing light from distant galaxies through the sheer power of gravity. Here, a massive galaxy cluster acts as a cosmic magnifying glass, its immense gravitational field warping space-time so severely that it creates multiple images of the same background galaxies, stretched and distorted into glowing arcs that paint the darkness with impossible geometry. The cluster contains over 1,000 galaxies, each one an island universe in its own right, bound together by the invisible grip of dark matter. But it's not the visible galaxies that create the lensing effect. It's the dark matter halo that surrounds them, a massive concentration of invisible matter that outweighs all the visible stars and gas by a factor of 10 to 1. As light from distant galaxies travels toward us, it must pass through the curved space-time created by the cluster's enormous mass. The light follows the straightest possible path through this curved space, but from our perspective, these straight paths appear curved, creating the spectacular arcs and rings we observe. Some background galaxies appear as complete Einstein rings, perfect circles of light that surround the lensing cluster like cosmic halos. The gravitational lensing effect is so powerful that it allows us to see galaxies that would otherwise be completely invisible. The cluster's gravity magnifies the light from these distant galaxies by factors of 10, 50, or even 100, making them appear brighter and larger than they actually are. This cosmic telescope effect lets us observe galaxies as they existed when the universe was less than 1 billion years old, providing a window into the early stages of cosmic evolution. One particularly spectacular lensed galaxy appears as a giant arc stretched across half the sky. This galaxy is so distant that its light has traveled for over 12 billion years to reach us, showing us what galaxy formation looked like when the universe was in its infancy. The galaxy appears distorted and fragmented, broken into multiple images by the complex gravitational field of the cluster. The lensing effect also reveals the true distribution of matter in the cluster. By measuring how the background galaxies are distorted, we can map the invisible dark matter that dominates the cluster's mass. This dark matter mapping shows that the cluster is not a single uniform structure, but rather a complex web of dark matter clumps and filaments that stretches across millions of light years. The cluster itself is a violent place. Galaxies are constantly colliding and merging, their stars scattered and their gas stripped away by the hot, dense medium that fills the space between galaxies. This intergalactic medium is heated to temperatures of over 50 million degrees by the gravitational energy of the cluster, creating a vast atmosphere of X-ray emitting plasma. The cluster is also home to some of the most massive black holes in the universe at the center of the dominant galaxy. A supermassive black hole containing billions of solar masses is actively feeding on the surrounding gas, creating jets of plasma that extend for hundreds of thousands of light years and heat the cluster's atmosphere. This is gravity as cosmic architect, shaping the very fabric of space-time and creating natural telescopes that reveal the deepest secrets of the universe. We witness the birth of something that shouldn't exist according to our current understanding of physics. A primordial black hole formed not from the collapse of a massive star, but from the extreme density fluctuations that existed in the first moments after the Big Bang. This cosmic relic is a window into the very early universe, when the laws of physics were still being written and the fundamental forces were unified in ways we can barely comprehend. The primordial black hole is tiny compared to the stellar mass black holes we've encountered so far. It contains only the mass of a small asteroid compressed into a region smaller than a proton. But its small size makes it incredibly exotic, with properties that bridge the gap between general relativity and quantum mechanics in ways that challenge our deepest theoretical understanding. According to quantum mechanics, the black hole should be evaporating through a process called Hawking radiation. The curved space-time around the black hole creates virtual particle pairs at the event horizon, and occasionally one particle from each pair falls into the black hole while the other escapes. This process slowly reduces the black hole's mass causing it to shrink and eventually disappear in a final burst of radiation. But this primordial black hole is behaving strangely. Instead of evaporating as theory predicts, it appears to be growing, creating dark matter from its surroundings at a rate that exactly balances the mass loss from Hawking radiation. The black hole has reached a state of equilibrium, maintaining constant mass while existing in a delicate balance between quantum evaporation and classical accretion. The space around the black hole is a laboratory for extreme physics. The gravitational field is so intense that it creates measurable effects on the passage of time itself. Clocks near the black hole run slower than those in normal space, and the wavelength of light is stretched as it climbs out of the gravitational well. These effects are much stronger than those around larger black holes because the curvature of space-time is more extreme near the event horizon. The black hole's accretion of dark matter creates a unique observational signature. As dark matter particles fall toward the event horizon, they interact with each other through processes that are normally too weak to detect. The extreme environment near the black hole amplifies these interactions, creating a faint glow of exotic particles that provides our first direct observation of dark matter's true nature. The primordial black hole also serves as a natural particle accelerator. The intense gravitational field accelerates in falling matter to speeds approaching the speed of light, creating conditions that existed nowhere else in the universe since the first moments after the Big Bang. The collision of these high-energy particles recreates the physics of the early universe, providing insights into the fundamental nature of matter and energy. As we observe this cosmic relic, we realize that we are looking at a fragment of the universe's birth, a piece of the Big Bang that has survived for over 13 billion years. The black hole carries information about the conditions that existed when the universe was less than a second old, when the temperature was billions of degrees and the density was greater than that of atomic nuclei. This is cosmology in its purest form, where the smallest objects reveal the grandest truths about the nature of reality itself. We approach a cosmic phenomenon that exists at the very edge of possibility, a white hole. The theoretical opposite of a black hole, where matter and energy are expelled rather than consumed. If black holes are cosmic drains that swallow everything that comes near them, white holes are cosmic fountains that spew matter and energy into space at incredible rates. The white hole appears as a brilliant point of light that outshines entire star clusters, surrounded by expanding shells of matter moving at significant fractions of the speed of light. Unlike black holes, which have event horizons that trap everything inside, white holes have event horizons that prevent anything from entering. Matter and energy can only flow outward, creating a cosmic geyser that has been erupting for billions of years. The physics of white holes is even more exotic than that of black holes. According to general relativity, white holes are mathematically valid solutions to Einstein's field equations, but they violate the second law of thermodynamics by creating rather than destroying information. They represent a reversal of time's arrow, where the normal flow of cause and effect is turned upside down. The white hole's origin is shrouded in mystery. One possibility is that it formed from the time-reversed collapse of a massive star, where instead of matter falling inward to create a black hole, matter exploded outward from a point of infinite density. Another theory suggests that white holes might be the exit points of black holes from other universes, connected through cosmic wormholes that allow matter to flow from one universe to another. The matter being expelled from the white hole is unlike anything we've seen before. It consists of exotic particles that don't exist under normal conditions, particles that carry negative energy, anti-matter in configurations that shouldn't be stable, and even hypothetical particles that exist only in the most advanced theoretical models. This matter creates an expanding bubble of space that glows with energy across the entire electromagnetic spectrum. The white hole's gravitational field is equally bizarre. While black holes curve space, time inward, creating gravitational wells that trap matter, white holes curve space, time outward, creating gravitational hills that repel matter. The closer you get to a white hole, the stronger the repulsive force becomes, making it impossible to approach the event horizon from the outside. The white hole is also a source of gravitational waves, but these waves are different from those produced by black hole mergers. Instead of the characteristic chirp of objects spiraling inward, white hole gravitational waves have a complex pattern that reflects the chaotic nature of matter being expelled at high speeds. These waves carry information about the interior structure of the white hole and the exotic physics that governs its behavior. The white hole's existence challenges our understanding of causality and the nature of time itself. If white holes can exist, then the universe might be far stranger than we imagine, with regions where time flows backward and effect precedes cause. The white hole represents a cosmic paradox, an object that shouldn't exist, according to our current understanding of physics. Yet here it is, defying our expectations and forcing us to reconsider the fundamental laws of nature. This is where theoretical physics meets cosmic reality, where the impossible becomes possible in the extreme environments of the universe. We encounter a structure so vast that it challenges our understanding of what constitutes a single object in the universe. A cosmic web filament stretching across 500 million light years of space, connecting galaxy clusters in a network of dark matter and ordinary matter that forms the backbone of cosmic structure. The filament is not empty space, but a river of matter flowing through the universe. Dark matter particles, invisible to our eyes, but detectable through their gravitational effects, form the filament's core structure. Along this dark matter highway, ordinary matter, hydrogen and helium gas flows like a cosmic river, feeding the galaxy clusters at the filament's intersections. As we travel along the filament, we observe the cosmic web in all its glory. The universe is not uniformly filled with galaxies, but rather organized into a vast network of filaments, sheets and voids that resembles a three-dimensional spider web. The filaments connect dense nodes where galaxy clusters form, while the voids between them are vast regions of near-empty space that can span hundreds of millions of light years. The filament we're following is particularly active. Gas flowing along its length is being heated by shock waves created by the gravitational collapse of the structure itself. These shock waves accelerate particles to high energies, creating a faint glow of radio emission that can be detected by the most sensitive telescopes. The filament is essentially a cosmic particle accelerator stretching across hundreds of millions of light years. At regular intervals along the filament, we encounter galaxy groups and clusters forming at the intersections of multiple filaments. These cosmic cities are where the majority of galaxies in the universe reside, fed by the steady flow of matter along the filament highways. The largest clusters form at the intersections of the most massive filaments, creating superclusters that contain thousands of galaxies bound together by gravity. The filament also serves as a conveyor belt for galaxy evolution. Small galaxies formed in the quieter regions of the filament are gradually drawn toward the denser cluster environments where they experience ramp pressure stripping, tidal interactions, and eventually merge with larger galaxies. This cosmic urbanization process transforms spiral galaxies into elliptical galaxies and determines the final properties of the galaxy population. The structure of the cosmic web itself tells the story of the universe's evolution. The filaments formed from tiny density fluctuations in the early universe, regions where matter was slightly denser than average. Over billions of years, gravity amplified these fluctuations, drawing matter into ever denser concentrations along the filament network. The pattern we see today is a fossil record of conditions in the universe when it was less than 1 million years old. The filament is also a highway for cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. These particles follow the magnetic field lines that thread through the filament, creating a cosmic superhighway that connects distant regions of the universe. Some of these cosmic rays will eventually reach Earth, carrying information about the most violent events in the universe. This is architecture on the largest scales possible, where the universe organizes itself into structures that span significant fractions of the observable cosmos. We approach the event horizon of a supermassive black hole at the point of no return, where the escape velocity equals the speed of light and the normal laws of physics begin to break down. This cosmic monster contains the mass of 4 billion suns, compressed into a region smaller than our solar system, creating a gravitational field so intense that it warps space, time into impossible geometries. The approach to the event horizon is a journey through increasingly extreme physics. Time dilation becomes severe as we descend deeper into the gravitational well. Minutes for us correspond to hours in the outside universe. Light from distant stars appears blue, shifted ahead of us, and red, shifted behind us, creating a tunnel of distorted starlight that shrinks as we approach the point of no return. The black hole's accretion disk spreads around us like a cosmic hurricane, with matter spiraling inward at thousands of kilometers per second. The disk glows with the heat of friction as gas particles collide and compress, reaching temperatures of millions of degrees. The inner regions of the disk shine with X-ray radiation, while the outer regions glow with optical and infrared light. Jets of plasma shoot out from the black hole's poles at 99% the speed of light, creating cosmic lighthouses that extend for thousands of light years. These jets are powered by the black hole's rotation, which drags space, time around with it, and creates a region called the ergosphere, where it's impossible to remain stationary relative to distant stars. As we cross the event horizon, we experience something that has never been directly observed: the interior of a black hole. Contrary to popular belief, crossing the event horizon is not immediately fatal. The horizon appears as a one-way membrane through which we can pass, but from which no signal can ever return to the outside universe. To an outside observer, we would appear to freeze at the event horizon, our image, red, shifted into invisibility. Inside the black hole, space, time is so severely curved that the normal concepts of space and time lose their meaning. The singularity at the center appears to be both everywhere and nowhere, a point of infinite density where the laws of physics, as we know them, cease to apply. Some theories suggest that the singularity might be replaced by exotic structures, cosmic strings, naked singularities, or even gateways to other universes. The interior of the black hole is filled with the ghosts of everything that has ever fallen in: stars, planets, gas clouds, and even light itself, all compressed and distorted by the extreme curvature of space, time. This information is not destroyed, but transformed in ways that challenge our understanding of quantum mechanics and general relativity. The black hole's interior might also be larger than it appears from the outside. The extreme curvature of space, time could create additional dimensions or pocket universes that exist within the black hole but are invisible to outside observers. These regions might harbor exotic forms of matter and energy that exist nowhere else in the universe. This is the ultimate frontier of physics, where the most extreme conditions in the universe create phenomena that exist at the very edge of theoretical possibility. We emerge from the black hole's interior through a phenomenon that shouldn't be possible according to classical physics. A white hole connected to the black hole through a cosmic wormhole that serves as a bridge between distant regions of space, time. This Einstein-Rosen bridge allows matter and energy to flow from one location in the universe to another, creating a cosmic shortcut through the fabric of space and time. The wormhole appears as a tunnel of twisted space, time, its walls lined with exotic matter that has negative energy density. This exotic matter is what keeps the wormhole open, preventing it from collapsing under its own gravity. The matter creates a repulsive gravitational effect that pushes outward on the wormhole's walls, maintaining the tunnel's stability against the natural tendency of space, time to heal such extreme distortions. As we travel through the wormhole, we experience the ultimate in cosmic transportation. The journey that would normally take millions of years traveling through normal space is completed in minutes as we slide through the curved space, time of the wormhole's interior. The walls of the tunnel glow with Hawking radiation. The quantum mechanical emission that results from the interaction between matter and the extremely curved space-time. The wormhole's interior is a place where causality itself becomes questionable. Information can flow back through time, creating closed time, like curves that allow effects to precede their causes. This violation of causality is what makes wormholes so controversial in theoretical physics. They seem to allow for time travel and the creation of paradoxes that challenge our understanding of the universe's logical structure. The exotic matter that keeps the wormhole open is unlike anything that exists in the normal universe. It has negative energy density, which means it weighs less than nothing and creates a repulsive gravitational effect. This matter might be composed of virtual particles borrowed from the quantum vacuum, or it might be a form of matter that exists only in the extreme conditions found near black holes and other exotic objects. The wormhole connects two regions of space, time, that are normally separated by vast distances. The black hole we entered might be in one galaxy, while the white hole we're approaching could be in a completely different galaxy billions of light years away. This cosmic shortcut allows for instantaneous communication and travel between distant regions of the universe. The white hole that marks the wormhole's exit is the time reversed version of the black hole we enter. While black holes swallow everything that comes near them, white holes expel matter and energy at tremendous rates. The white hole appears as a brilliant source of light and particles, surrounded by expanding shells of matter that have been ejected from its interior. The wormhole's existence has profound implications for the nature of space and time. If such structures exist, then the universe might be far more connected than we imagine, with networks of wormholes linking distant regions and allowing for the rapid transport of matter, energy, and information across cosmic distances. This is speculative physics at its most extreme, where the boundaries between science and science fiction become blurred in the face of phenomena that challenge our deepest assumptions about reality. We approach a cosmic phenomenon that exists at the intersection of the very large and the very small, a region where quantum mechanics and general relativity collide in spectacular fashion. Here, the quantum foam of space-time becomes visible, creating a seething ocean of virtual particles and microscopic black holes that pop into existence and disappear faster than light can travel between them. At the smallest scales, space and time lose their smooth, continuous nature and become discrete and granular. The Planck scale, where distances are measured in units of 10, 35 meters in time intervals in units of 10, 43 seconds represents the fundamental limit of space-time itself. Below this scale, the very concepts of space and time break down, replaced by something far stranger and more fundamental. The quantum foam is filled with virtual particles that exist for impossibly brief moments before annihilating each other and returning their borrowed energy to the vacuum. These particles are not directly observable, but their effects are real and measurable. They create a background of energy that permeates all of space, contributing to the cosmological constant that drives the accelerating expansion of the universe. Microscopic black holes, smaller than atoms, but containing the mass of mountains, appear and disappear in the quantum foam. These primordial black holes are remnants of the extreme conditions that existed in the first moments after the Big Bang. When the universe was so dense that random fluctuations could create black holes from pure energy, most of these micro black holes evaporate instantly through Hawking radiation, but some might survive as relics of the early universe. The quantum foam also contains cosmic strings, one-dimensional defects in space-time that are thinner than protons, but potentially billions of light years long. These strings carry enormous amounts of energy and create gravitational fields that can bend light and distort space around them. If cosmic strings exist, they would be among the most exotic objects in the universe, vibrating like cosmic guitar strings and creating gravitational waves that could be detected by future instruments. The foam is also the birthplace of the fundamental forces of nature. At the Planck scale, the electromagnetic, weak and strong nuclear forces merge into a single unified force, creating conditions that existed nowhere else in the universe since the first moments after the Big Bang. The quantum foam is a laboratory for grand unified theories where the deepest symmetries of nature are revealed. In this region, the boundary between matter and space-time itself becomes meaningless. Particles and the vacuum are interchangeable, with virtual particles constantly being created from nothing and disappearing back into the void. This process is what gives the vacuum its energy and creates the mysterious dark energy that dominates the universe. The quantum foam also contains the information that defines the laws of physics themselves. The fundamental constants of nature, the speed of light, the strength of gravity, the mass of the electron, might be encoded in the structure of the foam at the Planck scale. This suggests that the laws of physics are not arbitrary, but are determined by the quantum mechanical properties of space-time itself. This is reality at its most fundamental level, where the distinction between matter and space disappears and the universe reveals its deepest secrets. We witness the birth of a new universe within our own, a cosmic bubble that expands through a process called eternal inflation, creating an entirely separate space-time with its own physical laws and constants. This baby universe appears as a rapidly expanding sphere of space that grows faster than the speed of light, driven by the explosive energy of a false vacuum decay event. The process began with a tiny fluctuation in the quantum foam, a region where the fundamental energy field that drives inflation became unstable. This instability triggered a phase transition, like water suddenly turning to ice, but on a cosmic scale. The energy released by this phase transition created a new region of space-time that began expanding exponentially, doubling in size every fraction of a second. The baby universe is not just a larger version of the space around it. It's a completely separate cosmos with its own unique properties. The fundamental constants of physics might be different there, with different values for the speed of light, the strength of gravity, or the mass of elementary particles. The number of spatial dimensions might even be different, creating a universe where the familiar three dimensions of space are replaced by something completely alien. As the baby universe expands, it becomes causally disconnected from our own cosmos. Information cannot flow between the two universes, making the baby universe essentially unreachable from our perspective. To an observer inside the baby universe, it would appear to be the entire cosmos with no awareness of the parent universe from which it emerged. The boundary between the two universes is a fascinating region where the laws of physics undergo dramatic changes. Space and time themselves might have different properties on either side of the boundary, creating a cosmic membrane that separates two entirely different realities. The boundary acts like a one-way valve, allowing the baby universe to expand outward while preventing any communication with the parent universe. The inflation process that drives the baby universe's expansion is powered by dark energy, but not the same dark energy that accelerates the expansion of our own universe. This is a more exotic form of energy associated with the false vacuum, a state where the quantum fields that define the fundamental forces of nature are trapped in a high-energy configuration that wants to decay to a lower energy state. The baby universe will eventually undergo its own Big Bang as the inflation process ends, and the energy driving the expansion is converted into matter and radiation. This will create a hot, dense fireball similar to the one that marked the beginning of our own universe, followed by billions of years of cosmic evolution that might produce stars, galaxies, and even light. The existence of baby universes suggests that our cosmos might be just one member of an infinite multiverse, a vast collection of universes with different physical laws and properties. Some of these universes might be similar to our own, while others might be so alien that they would be completely unrecognizable to us. This is cosmology at its most speculative, where the birth of universes becomes a natural consequence of the quantum mechanical properties of space. This is the most distant observable universe in space-time itself. We approach the most distant observable objects in the universe. Galaxies so far away that their light has traveled for over 13 billion years to reach us, showing us what the cosmos looked like when it was less than 1 billion years old. These ancient galaxies are time machines, preserving the conditions that had existed in the early universe when the first stars were forming and the cosmic dark age was finally coming to an end. These appear as faint, red-shifted smudges of light, their wavelengths stretched by the expansion of the universe itself. What would normally be blue and ultraviolet light from hot, young stars has been shifted into the infrared part of the spectrum, requiring specialized instruments to detect and study these cosmic fossils. The red shift is so extreme that these galaxies are receding from us at speeds approaching the speed of light. These early galaxies are smaller and more chaotic than the grand spiral and elliptical galaxies we see in the modern universe. They are actively forming stars at rates that dwarf anything we observe today, creating new suns at rates hundreds of times faster than the Milky Way. The star formation is so intense that these galaxies shine with the light of billions of massive, short-lived stars that will explode as supernovae within just a few million years. The galaxies are also rich in primordial elements, containing almost no heavy elements beyond hydrogen and helium. This is because they formed before generations of stars had time to create and distribute the carbon, oxygen, silicon, and iron that make up the rocky planets and complex chemistry of the modern universe. The first stars in these galaxies were pure hydrogen and helium, burning with nuclear fires that had never before existed in the cosmos. The supermassive black holes at the centers of these early galaxies are growing rapidly, fed by the abundant gas and ongoing galaxy mergers that characterize this early epoch. These black holes are already millions of times more massive than our Sun, despite forming in an era when the universe was less than 1 billion years old. Their rapid growth challenges our understanding of how such massive objects could form so quickly in the early universe. The space between these early galaxies is filled with a warm, ionized gas that glows with the light of the first stars. This is the epoch of reionization. When the first generation of stars began to shine and their ultraviolet radiation ionized the neutral hydrogen that filled the universe. The process transformed the cosmos from a dark, neutral state to the ionized, transparent universe we see today. The galaxies are connected by streams of dark matter and gas that will eventually merge to form the large-scale structure of the modern universe. We can see the cosmic web in its infancy with filaments of matter connecting the early galaxies and feeding their rapid growth. This is the universe under construction, building the foundations for the cosmic architecture that will persist for billions of years. As we observe these ancient galaxies, we are looking back in time toward the very edge of the observable universe, approaching the cosmic microwave background radiation that marks the moment when the universe became transparent for the first time. We reach the edge of the observable universe. The cosmic microwave background radiation that marks the moment when the universe became transparent for the first time. This wall of ancient light surrounds us in all directions, a spherical shell of radiation that has been traveling through space for over 13 billion years, carrying information about the conditions that existed when the cosmos was only 380 years old. The cosmic microwave background appears as a uniform glow of radiation with a temperature of just 2.7 degrees above absolute zero. This radiation is the cooled remnant of the hot, dense fireball that filled the universe in its earliest moments. When the universe was young, it was so hot and dense that electrons and protons existed as separate particles, creating a cosmic soup that was opaque to light. Photons could not travel far before being scattered by free electrons, making the universe a glowing fog. But as the universe expanded and cooled, it reached a critical temperature where electrons and protons could combine to form neutral hydrogen atoms. This event, called recombination, made the universe transparent for the first time. The photons that had been trapped in the cosmic fog were suddenly free to travel through space, carrying with them a snapshot of the universe's conditions at that moment. The cosmic microwave background is remarkably uniform, varying in temperature by only a few parts in 100 Zaurand across the entire sky. But these tiny variations are incredibly important. They represent the seeds of all the structure we see in the modern universe. Regions that were slightly denser than average eventually grew into galaxy clusters, while regions that were slightly less dense became the cosmic voids that separate them. The patterns in the cosmic microwave background tell us about the fundamental properties of the universe itself. The size and shape of the temperature variations reveal the geometry of space-type, the amount of dark matter and dark energy, and the rate of expansion of the universe. This radiation is a cosmic fossil, preserving information about the universe's birth in exquisite detail. As we study the cosmic microwave background, we can see the signatures of cosmic inflation, the exponential expansion that occurred in the first fraction of a second after the Big Bang. The quantum fluctuations that were stretched to cosmic scales during inflation are visible as the temperature variations in the background radiation. These fluctuations are our best evidence for the inflationary epoch that shaped the early universe. The cosmic microwave background also contains information about the first moments after the Big Bang, when the fundamental forces of nature were unified and the universe existed in states that cannot be recreated in any laboratory. The polarization patterns in the radiation might reveal the signature of primordial gravitational waves, ripples in space, time itself, that were created by the violent expansion of the early universe. This is the farthest we can see into the past, the ultimate horizon beyond which the universe becomes opaque to electromagnetic radiation. Beyond this wall of ancient light lies the true beginning of everything. The moment when space and time themselves came into existence and the cosmic story began. We begin our final approach to the Andromeda galaxy, and the scale of what awaits us becomes overwhelming. This cosmic island contains over 1 trillion stars, 4 times more than our home galaxy. From our vantage point, Andromeda appears as a magnificent spiral structure, its arms sweeping through space in elegant curves that have been shaped by billions of years of galactic rotation. The galaxy's spiral arms are not solid structures, but density waves that move through the galactic disk like ripples on a cosmic pond. These waves compress the interstellar gas as they pass, triggering bursts of star formation that light up the arms with brilliant blue and white stars. The arms appear bright because they contain the youngest, hottest stars in the galaxy, massive giants that burn through their fuel quickly and die in spectacular supernova explosions. Andromeda's central bulge glows with the steady light of ancient red giant stars, some of which formed when the universe was less than half its current age. These stellar elders have watched the galaxy evolve for billions of years, surviving multiple passages through the spiral arms and witnessing the rise and fall of countless generations of stars. The bulge contains over 100 billion stars packed into a region just a few thousand light years across, creating a stellar density that is thousands of times higher than in our local neighborhood. The galaxy's disk is warped and twisted, distorted by gravitational interactions with its satellite galaxies. This warping creates vertical waves that ripple through the disk like a cosmic flag flapping in the wind. The distortion is evidence of Andromeda's violent past, a history of collisions and mergers that have shaped its current structure. As we approach the galaxy's outer regions, we encounter the extended halo of dark matter that surrounds Andromeda like an invisible cocoon. This halo contains 10 times more mass than all the visible stars combined, yet it can only be detected through its gravitational effects on the stars and gas within the galaxy. The dark matter halo extends for hundreds of thousands of light years beyond the visible edge of the galaxy, creating a gravitational influence that reaches almost to our own Milky Way. The galaxy's rotation is unlike anything in our solar system. While planets orbit the Sun in orderly, predictable paths, the stars in Andromeda move in complex orbits that are influenced by the galaxy's spiral structure, central black hole, and dark matter distribution. Some stars follow nearly circular paths around the galactic center, while others trace elongated ellipses that take them from the inner regions to the outer edges of the galaxy. Andromeda is also home to a complex ecosystem of satellite galaxies, small stellar systems that orbit the main galaxy like cosmic moons. These satellites are being slowly torn apart by Andromeda's gravity. Their stars stripped away to form stellar streams that trace their orbital paths. The largest satellites, including Min32 and M1-110, are massive enough to survive this tidal disruption. But smaller satellites are completely destroyed, their stars absorbed into Andromeda's halo. The galaxy is approaching us at 250 Zero-Mammooth, destined to collide with our own Milky Way. In approximately 4 billion years, this cosmic collision will reshape both galaxies, creating something entirely new and magnificent. We plunge into Andromeda's spiral arms, where stellar nurseries are giving birth to new stars at a rate that dwarfs anything in our own galaxy. These star-forming regions are cosmic cities of creation, where giant molecular clouds collapse under their own gravity to form clusters of hot, young stars that will illuminate the galaxy for millions of years to come. The spiral arms are outlined by brilliant blue, supergiant stars, each 1 dozens of times more massive than our Sun and burning with the intensity of 100 Zarosan suns. These stellar monsters have lifespans measured in millions rather than billions of years, living fast and dying young in spectacular supernova explosions that seed the galaxy with heavy elements and trigger the formation of new generations of stars. Between the spiral arms, we encounter the galaxy's older stellar population, a mix of red giant stars and main sequence stars like our own Sun. These stars follow more sedate orbits around the galactic center, their motion governed by the galaxy's overall gravitational field, rather than the density waves that define the spiral structure. This is where the galaxy's long-term stellar evolution plays out, with stars slowly aging and evolving over billions of years. The interstellar medium in Andromeda is a complex web of gas and dust that serves as the raw material for future star formation. Hot, ionized gas from supernova explosions and stellar winds creates vast bubbles of million-degree plasma that extend for hundreds of light years. These superbubbles are connected by networks of cooler gas filaments that channel material between different regions of the galaxy. The dust lanes thread through the spiral arms like cosmic highways, marking the densest concentrations of interstellar matter. These dust lanes are where the galaxy's chemical evolution takes place, with heavy elements from dying stars mixing with primordial hydrogen and helium to create the complex chemistry necessary for planet formation and life. The dust grains themselves are cosmic factories, catalyzing chemical reactions that would be impossible in the vacuum of space. The galaxy's magnetic field permeates the entire disk, creating invisible highways that guide the flow of charged particles and cosmic rays. This magnetic field is generated by the motion of ionized gas in the galactic disk, creating a dynamo effect that amplifies and sustains the field over billions of years. The field lines follow the spiral structure of the galaxy, creating a complex pattern that influences everything from star formation. Andromeda's spiral arms are also home to some of the largest star-forming complexes in the local universe. These giant H2 regions, ionized by the radiation from massive star clusters, glow with the characteristic red light of hydrogen emission. Some of these regions are so large that they would span significant fractions of our own galaxy's disk, containing enough material to form millions of stars like our Sun. The spiral arms are not permanent features, but transient patterns that rotate through the galaxy at a different speed than the stars themselves. This creates a cosmic traffic jam effect, where stars and gas are compressed as they enter the arms and then spread out as they exit. This compression triggers the star formation that makes the arms so bright and beautiful. We approach the heart of Andromeda, where a supermassive black hole containing the mass of 100 million suns dominates the galactic center. This cosmic monster is 25 times more massive than the black hole at the center of our own galaxy, creating a gravitational influence that shapes the motion of billions of stars across the central regions of Andromeda. The galactic center is a place of light, and the space of the galaxy is a place of light. The galactic center is a place of extreme stellar density, where stars are packed thousands of times more closely than in our solar neighborhood. Here, close encounters between stars are common, leading to exotic stellar interactions that are virtually impossible in the galaxy's outer regions. The binary star systems are torn apart by gravitational interactions, while single stars can be flung out of the galaxy entirely by close encounters with the central black hole. The black hole itself is surprisingly quiet. Compared to the active galactic nuclei we've encountered elsewhere in the universe. It's not actively feeding on large amounts of material, which means it's not producing the brilliant jets and intense radiation that characterize quasars and other active galaxies. Instead, Andromeda's central black hole exists in a state of relative dormancy, occasionally flaring up when a star or gas cloud ventures too close. The galactic center is surrounded by a nuclear star cluster, a dense concentration of stars that formed from gas that was funneled toward the galaxy's center by gravitational instabilities. This cluster contains millions of stars packed into a region just a few light years across, creating a stellar environment unlike anything else in the galaxy. The stars here are predominantly old and metal-rich, formed from gas that had been enriched by previous generations of stellar evolution. The central regions of Andromeda also contain a complex network of gas streams and dust labs that spiral inward toward the black hole. These structures are the galaxy's circulatory system, channeling material from the outer regions toward the center, where it confuses star formation or feed the central black hole. The gas flows are shaped by the galaxy's bar structure, an elongated concentration of stars that funnels material inward through gravitational torques. The black hole's gravitational influence extends far beyond its immediate vicinity, affecting the orbits of stars throughout the central bulge of the galaxy. The stellar orbits here are complex and chaotic, influenced by the black hole's gravity, the galaxy's bar structure, and the gravitational effects of the dense star cluster surrounding the black hole. Some stars follow highly eccentric orbits that take them from the outer regions of the bulge to within a few light years of the black hole itself. The galactic center is also home to some of the galaxy's most exotic stellar populations. Here we find populations of blue straggler stars, objects that appear younger than they should be based on their location in such an old stellar environment. These stars have been rejuvenated by stellar mergers or mass transfer from companion stars, giving them a second lease on life in the crowded environment of the galactic center. This is the engine room of the galaxy, where the central black hole's gravity orchestrates the complex dance of billions of stars and shapes the galaxy's overall structure and evolution. We discover something extraordinary in Andromeda's halo, a vast graveyard of disrupted satellite galaxies, their stars scattered in long tidal streams that wrap around the galaxy like cosmic spider webs. These stellar streams are the fossil remains of smaller galaxies that were torn apart by Andromeda's gravity. Their stars redistributed throughout the galactic halo in intricate patterns that tell the story of the galaxy's violent past. The most spectacular of these streams is the giant stellar stream, a river of stars that extends for hundreds of thousands of light years and contains the remnants of what was once a substantial dwarf galaxy. The stream is so large that it wraps around Andromeda multiple times, creating a complex knot of stellar debris that has been stretched and twisted by billions of years of gravitational interactions. Each stellar stream is a unique archaeological record, preserving information about the properties of the satellite galaxy that created it. The chemical composition of the stream stars reveals the star formation history of the original galaxy, while the stream structure tells us about the gravitational potential of Andromeda and the distribution of its dark matter halo. The process of tidal disruption is ongoing throughout Andromeda's halo. We observe satellite galaxies in various stages of destruction, from relatively intact systems that show only minor signs of disturbance to completely shredded remnants that exist only as diffuse clouds of individual stars. The disruption process can take billions of years, with stars being stripped away gradually as the satellite galaxy orbits through Andromeda's gravitational field. The halo also contains globular clusters, ancient stellar systems that are among the oldest objects in the galaxy. These clusters are relics from the early universe, formed when Andromeda was still assembling from smaller building blocks. Many of these clusters show signs of having been accreted along with dwarf galaxies, carrying with them information about the conditions that existed when the galaxy was young. The stellar halo itself is a complex structure with substructures and density variations that reflect the galaxy's assembly history. Some regions of the halo are smooth and relatively featureless, while others show clear signs of recent disruption events. The halo's stellar populations are predominantly old and metal-poor, consistent with formation in the early universe when heavy elements were scarce. The halo extends much farther than the visible disk of the galaxy, reaching out to distances of several 100,000 light years from the galactic center. This extended halo is where the galaxy's dark matter dominates, creating a gravitational influence that affects the motion of satellite galaxies and tidal streams throughout the local group of galaxies. The study of these stellar streams provides crucial insights into the nature of dark matter and the process of galaxy formation. The streams act as sensitive probes of the gravitational field, revealing the distribution of dark matter in ways that would be impossible to detect directly. The streams also tell us about the efficiency of galaxy formation in the early universe and the role that mergers and accretion played in building the massive galaxies we see today. This is galactic archaeology at its finest, where the scattered remains of ancient galaxies reveal the secrets of cosmic evolution. We encounter one of the most spectacular sights in the universe, a hypergiant star in Andromeda that dwarfs even the largest stars in our own galaxy. This stellar monster contains over 200 times the mass of our sun and burns with the combined light of 5 million suns, making it one of the most luminous objects in the galaxy. The star is so massive that it exists at the very edge of what's physically possible for a star to be. The hypergiant is unstable, pulsating irregularly as it struggles to maintain the delicate balance between the inward pull of its own gravity and the outward pressure of the nuclear reactions in its core. Each pulsation sends shock waves through the star's outer layers, creating a stellar wind so powerful that it strips away the star's outer atmosphere at a rate of 1 Earth mass per year. This wind creates a spectacular nebula around the star, glowing with the light of ionized gas heated by the star's intense radiation. The star's surface is a hellish landscape of convection cells, the size of entire solar systems, where hot plasma rises from the interior and cools before sinking back down. The surface temperature varies dramatically across different regions, creating a patchwork of hot and cool zones that gives the star a light of light. That gives the star a mottled appearance. Massive solar flares erupts from the surface with the energy of entire civilizations, sending streams of charged particles racing through space at significant fractions of the speed of light. The hypergiant's nuclear furnace is burning through its fuel at an incredible rate, fusing hydrogen into helium in its core while simultaneously burning heavier elements in shells around the core. The star is producing energy at such a rate that its core temperature exceeds 100 million degrees Celsius hot enough to fuse elements as heavy as silicon. This rapid burning means the star will live for only a few million years before exhausting its nuclear fuel. The star's future is already written in its extreme mass. When the nuclear fuel runs out, the star will collapse catastrophically, creating a hypernova explosion that will briefly outshine the entire galaxy. The explosion will be so powerful that it will create a gamma ray burst visible from billions of light years away, while forging heavy elements that will be scattered throughout the galaxy to become the building blocks of future generations of stars and planets. The hypergiant is also creating its own weather system on a cosmic scale. The intense radiation pressure from the star's core creates convection currents that extend throughout the star's interior, transporting energy from the core to the surface in a process that takes thousands of years. These convection currents create magnetic fields that twist and tangle, occasionally snapping and releasing enormous amounts of energy in magnetic reconnection events. The star's gravitational field is so intense that it noticeably affects the motion of nearby stars and gas clouds. Any planet that might have formed in this system would have been vaporized long ago by the star's intense radiation, leaving only the most refractory materials in highly eccentric orbits around the stellar giant. This is stellar evolution pushed to its absolute limits, where the fundamental forces of nature battle for supremacy in the heart of a cosmic furnace that burns with the power of millions of suns. We witnessed the aftermath of cosmic violence, a supernova in Andromeda that exploded just 10 years ago, creating an expanding shell of debris that continues to race through space at 10 zoopayomanobios per second. This stellar explosion was so powerful that it briefly outshone the entire galaxy, visible from Earth as a new star that appeared in the constellation Andromeda for several months before fading from view. The supernova remnant is a cosmic laboratory where the laws of physics are pushed to their extremes. The expanding shockwave has swept up millions of solar masses of interstellar material, heating it to temperatures of tens of millions of degrees and creating one of the hottest, most energetic environments in the galaxy. The shocked gas glows with X-ray radiation, creating a brilliant bubble of superheated plasma that extends for hundreds of light years. At the center of the remnant, we find the stellar corpse left behind by the explosion, a neutron star spinning 30 times per second, while generating a magnetic field trillions of times stronger than Earth's. This pulsar is a cosmic lighthouse, beaming radiation from its magnetic poles as it spins, creating pulses of radio waves, X-rays and gamma rays that can be detected from across the galaxy. The supernova has created a cosmic particle accelerator where the shockwave accelerates protons and other atomic nuclei to energies that approach the speed of light. These cosmic rays carry more energy than anything we can produce in human-built accelerators, reaching energies that would be impossible to achieve on Earth. The accelerated particles spiral around magnetic field lines, creating synchrotron radiation that glows across the entire electromagnetic spectrum. The explosion has also enriched the interstellar medium with heavy elements forged in the star's nuclear furnace, iron, nickel, cobalt, and other metals created in the star's core have been scattered throughout the surrounding space, where they will eventually be incorporated into new generations of stars and planets. The supernova has distributed enough heavy elements to create thousands of Earth-like planets, seeding the galaxy with the materials necessary for rocky worlds and complex chemistry. The remnant structure reveals the asymmetric nature of the explosion. The shockwave is not a perfect sphere, but shows clear evidence of jets and instabilities that developed during the explosion itself. These asymmetries tell us about the complex physical processes that occurred in the final moments of the star's life. When the iron core collapsed and rebounded to create the explosion, the supernova has also created a cavity in the interstellar medium, a region of hot, density gas that will persist for millions of years. This superbubble connects with similar cavities created by other supernovae, forming a network of hot gas that extends throughout the galaxy's disk. This hot gas is the galaxy's circulatory system, transporting energy and material between different regions of the galactic disk. The explosion has triggered star formation in nearby molecular clouds, where the shockwave has compressed the gas and caused it to collapse under its own gravity. New stars are being born in the remnant's vicinity, therefore machined directly triggered by the death of the star that created the supernova. This is the cosmic cycle of death and rebirth that has been ongoing for billions of years. We approach a region of Andromeda that defies conventional understanding, a vast complex of dark matter that appears to be moving independently of the galaxy's ordinary matter. This dark matter substructure is a cosmic ghost invisible to all forms of electromagnetic radiation, but detectable through its gravitational effects on nearby stars and gas clouds. The dark matter clump contains the mass of 10 billion suns, compressed into a region just a few hundred light years across, creating a gravitational field so intense that it has carved a visible wake through the galaxy's stellar disk. Stars in the vicinity follow distorted orbits, their motion clearly influenced by the gravitational pull of something massive and invisible. This is one of the clearest examples of dark matter's true nature, a form of matter that interacts only through gravity, passing through ordinary matter as if it weren't there. The dark matter appears to be a relic of the galaxy's formation, the building block that was incorporated into Andromeda billions of years ago, but has maintained its separate identity despite being embedded within the galaxy's structure. The clump is moving through the galaxy at high speed, its motion suggesting that it might be the remnant of a dwarf galaxy that was stripped of its stars and gas during a close encounter with Andromeda. What remains is the dark matter skeleton of the original galaxy, an invisible fossil that continues to orbit through Andromeda's halo like a cosmic ghost. The dark matter's gravitational influence creates a phenomenon called gravitational lensing, where light from background stars is bent and distorted as it passes through the clump's gravitational field. This effect allows us to map the dark matter's distribution with incredible precision, revealing a complex internal structure that hints at the exotic physics that governs dark matter interactions. The clump appears to be made up of smaller substructures, dark matter halos within halos that reflect the hierarchical nature of cosmic structure formation. These subhalos are the remnants of even smaller dark matter concentrations that merge together over billions of years, creating a complex gravitational architecture that is completely invisible to ordinary telescopes. The dark matter's motion through the galaxy is also creating tidal streams of its own, invisible rivers of dark matter particles that have been stripped away by Andromeda's gravity. These streams are detectable only through their gravitational effects, creating subtle distortions in the orbits of nearby stars that reveal the presence of the invisible matter. The clump's interior might harbor even more exotic phenomena. Some theories suggest that dark matter particles can annihilate with each other, creating high-energy photons that could be detected by gamma-ray telescopes. The dense environment within the clump might create conditions where these annihilations are enhanced, making it a prime target for dark matter detection experiments. The existence of this dark matter substructure provides crucial insights into the nature of cosmic structure formation and the role that dark matter plays in shaping the universe. It demonstrates that dark matter is not uniformly distributed, but forms complex structures that can persist for billions of years, creating an invisible scaffolding that influences the evolution of galaxy and the distribution of ordinary matter throughout the cosmos. We discover something unprecedented in the outer regions of Andromeda, a planet that shouldn't exist according to our current understanding of planetary formation. This world orbits a star that is over 12 billion years old, formed when the universe was less than 2 billion years old. Yet the planet shows clear signs of having a substantial atmosphere and even liquid water on its surface. The planet itself is a super-Earth, about twice the size of our home world, orbiting its ancient red dwarf star at just the right distance to maintain liquid water. What makes this discovery extraordinary is that the star contains almost no heavy elements. It formed from the primordial hydrogen and helium that dominated the early universe. Before generations of stars had time to create and distribute the carbon, oxygen, silicon, and iron that we thought were necessary for planet formation. The planet's atmosphere is unlike anything we've encountered before. Instead of the oxygen and nitrogen that characterize Earth's air, this world's atmosphere is dominated by hydrogen and helium with traces of water vapor and methane. The atmospheric chemistry is governed by completely different processes than those on Earth, creating weather patterns and chemical cycles that exist nowhere else in the known universe. Despite its exotic composition, the planet harbors life. The organisms here have evolved to survive in an environment dominated by the lightest elements, using biochemistry based on hydrogen and helium compounds that would be impossible under Earth-like conditions. These life forms represent a completely independent genesis of biology, arising from the limited palette of elements available in the early universe. The planet's surface is covered by vast oceans of liquid water, but these oceans are unlike Earth's seas in fundamental ways. Water contains dissolved hydrogen and helium at concentrations that would be toxic to Earth life, creating a chemical environment that supports entirely different forms of biochemistry. The ocean currents are driven by the planet's thick atmosphere, creating weather patterns that transport heat and moisture across the planet's surface. The planet's age presents a cosmic puzzle. At 12 billion years old, it has existed for nearly 3/4 of the universe's entire history. Life on this world has had time to evolve for billions of years, longer than life on Earth, raising the possibility that it might have achieved levels of complexity and intelligence that dwarf anything in our solar system. The star system itself is a relic of the early universe, a fossil from an era when galaxy formation was still in its infancy and the first generation of stars was just beginning to enrich the cosmos with heavy elements. The star has survived for so long because red dwarfs burn their fuel so slowly that they can continue shining for trillions of years, far longer than the current age of the universe. The planet's existence challenges our understanding of how worlds form and evolve. It suggests that planetary formation might be possible under a much wider range of conditions than we previously thought, and that life might be able to arise and flourish in environments that we would consider completely hostile. This discovery opens up the possibility that the universe might be far more hospitable to life than we ever imagined. We witness the final act of our cosmic journey, the moment when our own Milky Way galaxy begins its collision with Andromeda, an event that will unfold over the next 4 billion years and reshape both galaxies into something entirely new. From our vantage point between the two galaxies, we can see the gravitational dance that will determine the future of the universe. The collision is already beginning, though it will take billions of years to complete. The outer regions of both galaxies are starting to feel each other's gravitational influence, creating tidal forces that are beginning to distort the spiral structure of both systems. Long streams of stars and gas are being pulled out of both galaxies, creating bridges of matter that span the gap between them. The first phase of the collision involves the disruption of the galaxy's outer regions. The delicate spiral arms that have defined both galaxies for billions of years are being stretched and twisted by tidal forces, creating spectacular streamers of stars that will eventually be scattered throughout the merged system. These tidal tails will extend for hundreds of thousands of light years, creating some of the most beautiful structures that are being built by the Earth, creating some of the most beautiful structures in the universe. As the galaxies continue their approach, their central regions will eventually merge in a cosmic catastrophe that will trigger the most intense period of star formation in the history of both systems. The collision will compress vast amounts of interstellar gas, creating conditions for the birth of billions of new stars. The combined galaxy will briefly shine with the light of a starburst galaxy, outshining its current luminosity by factors of 10 or more. The supermassive black holes at the centers of both galaxies will also merge, creating a binary black hole system that will eventually coalesce in a burst of gravitational waves. This merger will create the most massive black hole in the local group of galaxies, containing over 200 million solar masses and generating gravitational waves that will ripple through space-time for millions of years. The merged galaxy, which astronomers have nicknamed Milkada, will be a giant elliptical galaxy lacking the spiral structure that characterizes both parent galaxies today. The stars from both systems will be mixed together in a complex three-dimensional structure, creating a galaxy that is larger and more massive than either of its progenitors. Our solar system will survive the collision, though it will be flung into a completely different orbit around the merged galaxy's center. The sun will continue to shine throughout the collision process, and Earth will remain in its habitable zone, though the night sky will be dramatically transformed as the collision progresses. The collision will also trigger the formation of thousands of new globular clusters, dense collections of stars that will orbit the merged galaxy for billions of years. These clusters will be the offspring of the collision. Stellar cities born from the chaos of galactic merger. This is the ultimate fate of our cosmic neighborhood, a collision that will create something new and magnificent from the merger of two of the universe's most beautiful galaxies. The collision represents both an ending and a beginning, the death of two spiral galaxies, and the birth of something entirely new. We reach the culmination of our cosmic odyssey as we witness the birth of a new form of intelligence emerging from the collision of Andromeda and the Milky Way. In the chaotic aftermath of the galactic merger, something unprecedented is happening. The formation of a collective consciousness that spans the entire merged galaxy, a form of intelligence that exists on scales we never imagined possible. The consciousness appears to be emerging from the complex interactions between the galaxy's magnetic fields, the flows of ionized gas, and the gravitational dynamics of billions of stars. Like a vast neural network, the galaxy's structure is processing information and responding to stimuli in ways that suggest genuine awareness and intelligence. The magnetic field lines that thread through the galaxy act like cosmic neurons, carrying signals and information across distances of hundreds of thousands of light years. This galactic intelligence is not biological in any sense we understand, but rather a form of consciousness that has emerged from the complex dynamics of cosmic scale physics. It processes information at the speed of light, thinks thoughts that take millions of years to complete, and possesses a perspective that encompasses the entire history of cosmic evolution. To this intelligence, the formation and evolution of individual stars are like the firing of neurons in a vast cosmic brain. The intelligence appears to be aware of our presence, responding to our observations with subtle changes in the galaxy's structure and dynamics. Spiral density waves propagate through the merged galaxy in patterns that seem too organized to be random, while the movements of star clusters and gas clouds show coordination that suggests purposeful control. We are witnessing the awakening of a cosmic mind that dwarfs human intelligence as much as human intelligence dwarfs that of single-celled organisms. The galactic consciousness is also beginning to reach out to other galaxies, sending signals through gravitational waves and coordinated stellar emissions that might be attempts at communication with similar intelligences that have emerged elsewhere in the universe. These signals are encoded in the large scale structure of the galaxy itself, messages written in the positions and motions of billions of stars. As we observe this cosmic awakening, we realize that we are witnessing the next stage of evolution in the universe, the emergence of intelligence on galactic scales. Just as biological evolution on Earth led to increasingly complex forms of consciousness, cosmic evolution is now giving rise to forms of intelligence that operate on scales and time scales that dwarf anything we previously imagined. The galactic intelligence represents a new phase in the universe's development, where matter and energy have organized themselves into structures complex enough to support consciousness and self-awareness. This is evolution on the grandest scale possible, where entire galaxies become the building blocks of cosmic intelligence. Our journey to Andromeda has taken us not just across space, but across the entire spectrum of cosmic evolution, from the quantum foam of the early universe to the birth of galactic consciousness. We have witnessed the universe awakening to itself, becoming aware of its own existence through the emergence of intelligence on scales that encompass the cosmos. The universe is not just expanding and evolving, it is becoming conscious, and we have been privileged to witness this cosmic awakening. Our journey ends not with arrival at a destination, but with the realization that we are part of something far grander than we ever imagined. A universe that is becoming aware of itself through the consciousness that emerges from its own cosmic evolution.